everyone, it's Justin again. In the last video, we learned how to calculate average rate of change. But we also learned that sometimes it follows the function's graph well, and other times, not so much. In this video, we'll learn when and why average rate of change can be useful despite its apparent flaws. Let's do an easy example first. Micah spends his afternoon on a hiking trail. The function f of h models the distance he hikes over time. What was his average hiking speed during the first 4 hours? Before we can read the graph, we need to know the input and output. How far he's hiked depends on how long he's been hiking. So the number of hours he's been hiking is the input, and the distance is the output. So now we can see that as time goes on, the distance he's hiked increases. How can we find his average speed during the first 4 hours? The first thing to notice is that the distance he covers each hour is different. During the first hour, he hiked 3 miles. The next hour, he slowed down and only hiked 1 mile. The next hour, he only went half a mile, then 1 mile. And from hour 4 to 5, Micah must have been resting because he didn't move at all. So with all these different speeds, how can we choose a single speed as our answer? That's why we use average rate of change. If the rate keeps changing, use one big rate that covers everything. We need the average rate of change in the first 4 hours, so we only need the interval from 0 to 4. On that interval, the graph rises 5.5 miles and runs 4 hours. If we simplify, 5.5 divided by 4, it comes out to 1.375 miles per hour. This is an average of all of his speeds on the hike. Sometimes he was going faster, other times he was going slower, but altogether Micah was going about 1.375 miles per hour. G of t models the gas in Hannah's car after she drives for some amount of time. How quickly does her car use gas between 3 hours and 9 hours of driving? Yet again, we can look at this graph and see that the rate of change, or slope, changes over the course of the graph. So we can't use one single slope here. Instead, we're going to need to use an average rate of change over the interval from 3 to 9. It'll give us the slope of this line, which is a decent estimation of the function. The rise, or fall in this case, is -5, and the run is 6. So the slope of the line connecting these 2 points is -5/6. That's also the average rate of change on the interval. So our answer is that between 3 and 9 hours of driving, Hannah's car used an average of 5/6 of a gallon per hour. The local campground keeps track of how many campers they have and the highest temperature in Fahrenheit each day. According to the data collected in the table below, what is the average change in number of campers as temperature increases from 60 degrees to 90 degrees? This time we're using a table instead of a graph, but the concept is the same. Instead of getting worried over the different rates of change on each interval, we focus on the endpoints of the interval and just find the average rate of change. Rise over run doesn't make much sense without a graph, so we're going to use the actual slope formula here. Second output minus first output over the second input minus the first input. Simplify the numerator and the denominator, and then reduce the fraction. We could read this as 2/3 of a camper per degree, but it's kind of weird to say 2/3 of a person. So instead, we can split the numerator and denominator and read it as, on average, there are 2 more campers whenever the temperature increases 3 degrees. Slope is great for finding speed on linear functions, but in real life, most situations aren't linear. Everything is constantly speeding up and slowing down. So if we want to measure speed from one point to another, we calculate the average rate of change instead. In the next lesson, we're going to learn how to switch the input and output of a function by finding what's called an inverse. See you then.